All right, let's dive in. We hear about AI all the time, right? But today, we're going to peel back the layers and look at how it really works. And I don't just mean the code. I mean all the way down to the bare metal, the physics. Let's get into it. It really can feel like magic. You type a few words into a box, hit enter, and boom, a poem appears. But what's happening in that split second between your request and its answer? There's a whole universe of stuff happening under the hood. So let's pull back the curtain and see how the trick is actually done.
Okay, so this is our roadmap. It's called the AI system stock. Think of it like climbing a mountain. We're starting at the very bottom, at the level of raw physics, and we're going to work our way up, layer by layer, all the way to the AI apps you use every day.
So our climb starts right here, at the absolute foundation of everything. This is where the real magic begins. Turning something as basic as humble silicon, basically just super purified sand, into the microscopic brains that power this whole thing. Okay, so the magic word here, the most important word on this slide, is controlled. Think about it. A copper wire always lets electricity flow, and a piece of rubber never does. But silicon, it's special. It's a semiconductor. That means we can tell it, hey, turn on, or hey, turn off. And that control, that ability to flip the switch, that's the secret sauce for everything that comes next. So how do we actually get that control? Well, it's through this really clever process called doping. Seriously, it's almost like a baker adding just a pinch of yeast to flour to completely change what it can do. By sprinkling in just the right amount of other elements, we create two flavors of silicon. One type gets extra electrons that are just itching to move around, and the other type gets these little holes that are ready to catch them. That simple setup is all we need to create a perfect little electrical switch. And all of that work, all that doping and chemistry, it gives us this, the transistor. This is the fundamental building block of every single computer chip on the planet. It's really just a tiny switch. When we apply a little bit of voltage, zap, the switch turns on, current flows, and we call that a 1. Turn the voltage off, the current stops, and that's our 0. Ones and zeros. Every single thing a computer does, from sending an email to generating a poem, starts right here with billions of these simple on-off decisions. But here's where it gets absolutely mind-bending. The scale. You've probably heard of Moore's law, this idea that we just keep doubling the number of transistors we could cram onto a chip. Well, it happened. And it led to this. We're talking about more than 2 trillion of these tiny, tiny switches on a single modern AI chip. It's just a staggering number to even think about. Okay, so we've got trillions of these little switches. Awesome. But now what? We need to organize them into powerful engines that can actually do something. And it turns out, for the kind of work AI needs to do, the processor you have in your laptop, well, it's just not the right tool for the job. Let's move up the stack and see why. And here's the key difference. Your CPU, the processor in your computer, think of it like a couple of brilliant, super fast managers. They're amazing at handling complex jobs one after another in a sequence. But a GPU, that's totally different. It's like a giant factory with thousands of workers on an assembly line. Each worker just does one simple, repetitive task, but they all do it at the exact same time. AI is much more like that factory work. And TPUs, they're like that same factory, but with custom-built robots designed to do one and only one job perfectly. And that right there, that idea of doing thousands of things at once, has a name: parallelism. It is the absolute key. A GPU's entire design is built for this. It takes a massive math problem, smashes it into thousands of tiny little pieces, and tells all its little cores to solve their piece at the same time. That's exactly the kind of massive parallel power that modern AI needs. Because here's the thing you have to understand about AI. Underneath all the fancy words, what is it? It's math. Specifically, a type of math called linear algebra. It's basically just doing tons and tons of simple multiplications and additions, over and over and over again. And what's the perfect tool for doing thousands of simple calculations all at once? Yep, the GPU. Okay, so we've got our engines, we have these incredible parallel processing machines. But an engine is useless without a blueprint, right? We need the software, the actual instructions that tell these powerful engines what to do. So now we climb from the physical hardware into the abstract world of algorithms. And in the world of modern AI, there is one master blueprint that changed everything. It's called the transformer. It's just a special way of designing a neural network that turned out to be unbelievably good at spotting patterns in things like language. Seriously. Pretty much every big AI you hear about today, it's built on this fundamental design. Now, inside that transformer architecture, at its very heart, is this little piece of math. And don't worry, you don't need to be a math genius to get the big idea here. This is what's called the attention mechanism. All this formula really does is let the model look at a whole sentence and figure out which words are the most important to pay attention to. It's how it understands context, instead of just seeing a jumble of words.
So that's the blueprint. But how does the AI actually learn anything? Well, it's a pretty straightforward loop that just gets repeated billions of times. It's exactly like you setting flashcards for a test. First, you make a guess. That's the forward pass. Then you check the answer and see how wrong you were. That's the loss calculation. You think about why you got it wrong. That's back propagation. And finally, you adjust how you think so you'll do a little better next time. That's the weight update. Now, just imagine doing that billions of times a second. That's AI training.
All right, we're at the top of the mountain, the final layer of our stack. Because here's the reality. The most powerful AI models today are, well, they're just too big. They're way too massive to fit on just one chip, even a super powerful one. So we have to go even bigger. We have to connect thousands of these chips together to create one single massive AI brain. And, there are some really clever strategies for doing this. For example, with data parallelism, you give every chip the same AI model, but each one gets a different chunk of the data to work on. Or if the model itself is just too gigantic, you do model parallelism. You literally have to chop up the AI brain into pieces, and each chip only holds one piece of the puzzle. Or you can create an assembly line, where one chip does the first step of a calculation and passes its result to the next chip for step 2, and so on. But none of this works, none of it, unless all those thousands of chips can talk to each other instantly. The connections between the chips are every bit as critical as the chips themselves. These super fast networking technologies are like the nervous system connecting all of these digital neurons, letting them all act as a single coherent mind. And that's it. We've done it. We've climbed the entire stack. We started all the way down with the physics of a piece of silicon. We saw how that becomes transistors, how those form chips, how those chips run neural network models, and finally, how we connect thousands of them together into these enormous systems. So let's just look at that whole flow one more time, from beginning to end. You start with the laws of physics. That lets you build transistors. The transistors are built into chips. The chips run the math of neural networks. Those networks use incredible blueprints like the transformer. And that is what powers the intelligent applications that are literally changing our world.
I mean, when you really stop and think about it, it's just staggering, isn't it? We have literally figured out how to take common rock, sand, and through this incredible chain of innovation, turn it into a mind, a system that can create, that can reason. So the question for us now isn't just about the how anymore. We figured that out. The real question is, what are we going to ask it to do next?